Alrighty. So here we see a couple of literals. They've highlighted one. Are there any other literals in here? What are literals? Those are values that are hard-coded into the program. 20 is hard-coded into the program. Nothing's ever going to change that 20 until some other programmer comes in and changes it. There's a couple more, but they're not numbers. Well, I see one more number. Where's the other number? The other integer literal.
Return 0?
Yeah, that's one. This is a string literal. Today we sold and bushels of apples. If you ever hear me use the word literal, that's just all it means. Is it's a number or a string typed directly into the program. There's the string literals. Identifiers. This program here has a couple of identifiers. The ones we're most worried about are variable names and function names. There's another one. The namespace is another form of identifier. But it's just a name. Variables are the most commonly used identifiers. You know, you write a lot more variables than you write a lot of functions. But you use them both. But they follow the same naming rules. The naming rules are... Did we already discuss the variable naming rules? Okay. 1, cannot be a keyword. So don't say if or integer if is equal to 3. What would that even mean? But anyways, float while is equal to 4. That kind of stuff. None of that's going to work. You're very rarely going to even be tempted to do that. But if you did, you'd compile it and you'd get an error and you fixed it. There are some keywords that may be, you know, more tempting to use than others. Let's find a list of C++ keywords. Really? No. Take one more stab at it. There's a whole bunch of keywords. Way more than we're going to cover. There's one, you know, you might want to use the word class. Now, what class am I in? I'm, you know, in the 2017 class, something like that. Event, yeah, you might be tempted. I'm not seeing a lot of others. You just have to avoid using them as variable names. If you mess up, like I said, you'll get an error. A very obvious one. There are other rules. 2. They can only be letters, digits, or underscore or $sign. We can try out a few other examples and see if they work or not. Let's go into here, file, new project. I need to get my boilerplate out. Tired of typing all that stuff in the same. There we go. Add new item, C++ file. Here we go. Alrighty, so you know, integer a is okay. Integer a1 is okay. Let's try integer a1 underscore. That's okay. Integer a1 underscore $sign. That's cool. Integer a1 underscore $sign plus. Why is that going to be bad? Well, for one thing, it added a space there. But plus serves a very, you know, it's already got a purpose. It would think that we are trying to add two variables together. The textbook says don't use $sign as a variable name. I'm never tempted to do so, but basic programmers in the 70s used them all the time because that's how you define strings. So if you ever walked up to some code and you saw this string name $, you know that they were a basic programmer in the 70s. But otherwise, you don't really need to use $, but you could if you wanted to, you know. What is my pay rate? Pay rate, $. You know, whatever. You could do that. There are some specifics, though, about the numbers and the letters. It can't start with a number. Int 1a. That's a bad variable name. It's going to underline it to tell us it's wrong. How about starting with a $? Yeah, that's okay. It's just numbers that it cannot start with, which also implies that it can't be a number all by itself. What about some of those weird symbols that we can get by typing alt values? Int a, and then I'm going to type in alt 123. Okay, a musical note.
Calling back on that variable name would be hard
Uh-huh. Here, it's giving me a warning when I tried to save it. It says some Unicode characters could not be saved in the current code page. Do you want to resave this file as Unicode in order to maintain your data? I'm going to choose yes. And then I'm going to try to actually use that variable. A musical note is equal to 1 plus 2. Okay. It kind of makes sense that it supports doing that, because what if you're programming and, you know, you write in, you know, Hindi or Farsi or, you know, Kanji or, you know, Russian or whatever, and you're using letters that you know, just aren't here, that we're not expecting to see. People, you know, ought to be able to create variable names in their own language. So it looks like C++ is supporting Unicode character sets and not just ASCII. That's kind of cool. If we go and look at this source code with a text file editor, let's go see what it looks like. I'm going to right click over here and do Open Folder in File Explorer, find that CPP file. I'm going to try to edit it with Notepad just to see what it looks like. Oh, what do you know? Same thing. Whatever. Okay. So anyways, you can use weird symbols like that, but then your fellow programmers will hate you. So don't. What if you did this? Int 124 127 is equal to 3. I never thought about that. I could use a smiley as a variable name. Nah, you're just going to use letters, numbers, and underscores pretty much. And unless you have a keyboard that lets you easily type these other things for your own language of choice, then I wouldn't bother trying to get squirrely like that. Three cannot start with a number. 4, $sign looks weird, and the text says it doesn't work. Uncommon. Some languages just don't support the $sign. So identifiers, those are the programmer identified names. You get to pick those. When you're writing the program, part of the fun is that you get to pick the variable names. If you're going to ask somebody for their pay rate and then for the hours worked, you could be stingy with your variable names and do this. Float pay rate is equal to 10. Float hours worked is equal to, 40. Your goal in life is not to write the shortest variable names possible. Try to make them make sense. Those are okay, but it'd be a lot better to do pay rate is equal to 10. And then float hours worked is equal to 40. That makes the code a lot easier to read. But the variable names, in one sense, don't matter. If I do this, float total is equal to pay rate times hours worked, I would get the same answer whether I called it pay rate, hours worked, and total, or if I called them Spidey, and Iron Man. And so Iron Man is equal to Thor times Spidey. It works. It's goofy, but it works. Why? Because the language doesn't care what your variable names are as long as they're legal variable names. They're just for you. You know. So you get to call them whatever you want. When I'm typing code up here, I will tend to use single letter variable names. Don't use single letter variable names when you're writing your own code or you're a professional coder because they don't mean anything. The exceptions being if it's just a simple counter. You know, if you're just counting from 1 to 10 or 1 to 100 or, you know, whatever, yeah, why not? Why not just call it X? Otherwise, use words. Pay rate is equals to hours worked, that kind of stuff. The better your variable names are, the more, quote, self-documenting your code is. The fewer comments you have to add to your code in order for it to make sense. Here's a list of keywords too many to look at. It should represent the purpose of the variable. Items ordered. That's a lot better than just I/O, you know. What would I/O mean? I would think that I/O means input-output. You know, I've heard that phrase too many times. So the purpose of the variable is to hold the number of items ordered. So a variable holds, you know, data. So a variable has a name, a type, and a value. Try to give them good names. Meaningful names. Items ordered is a lot better than I/O. Now, did I do the bit where I talk about underscores versus capital letters yet? Alrighty. So if you have something like this, hourly pay rate, or you have hourly underscore pay underscore rate, you can use either one of those totally acceptably. I mean, you can't mix and match them. You know, once you pick one, you got to go with it. But some people try to make their variable names clear by adding underscores. Some people try to make them clearer by using uppercase letters. This is known as camel case because you have some capital letters in them and it puts humps in your words. And I didn't make that up. This is more kind of old school. Back in olden days, before programming languages supported both uppercase and lowercase letters, they may have been all uppercase. And if hourly pay rate was all in uppercase, it might be harder to read than if you wrote hourly underscore pay underscore rate. So this is kind of discouraged, and this has pretty much become the standard. Camel case has. For programs you write in here, I'm not going to count you off for whichever style you use. But I do want you to use good variable names rather than just H for hourly pay rate. Unless you're just doing an in-class assignment. Do as I say, not do as I do. Because like I said, sometimes I will use single letter names just to make it easy for y'all to type. Identifier rules. It can be an alpha character or an underscore or a $sign. After the first character, you can use alpha characters, numbers, or underscores. And upper and lowercase characters are distinct. And if you ever want to be a jerk, you could do things like this. Let's see. Pay rate 1. And then later on you do pay rate lowercase l. And you give them two different values. Don't make variable names that are very difficult to tell apart. Other things that are difficult to tell apart are O's and zeros. You know, pay rate 0 as opposed to pay rate O. This font is kind of showing them as different, but you know, some fonts don't make them look different at all. Or it'll put a slash through the 0 and not through the O or whatever. So, unless your goal is to deliberately torment your coworkers, don't pull stunts like mixing up lowercase l's and 1s just to freak people out. But they do mean different things. I mean, it is sensitive to uppercase letters. If I do this, int pay, and then I try to do pay is equal to 3, that's not going to work. The case is sensitive. because as far as a computer is concerned, a lowercase p is definitely different than an uppercase P. Integer data types. We know what integers are. It turns out there's a whole bunch of different kinds of integer data types. And the reason for that is that C and C++ have been around forever. So there are short ints, which are 16 bits, 2 bytes. There are unsigned short ints. Did I talk about the difference between short and signed and unsigned values? Nope. All right. Then there are normal ints, which are 4 bytes. And then there are long ints, which are also 4 bytes. Why are they the same? Then there are long ints, and this is the silliest one in the world except for this one. Unsigned long int. That's about the time where you think that they should redo it. And so when Microsoft came up with C#, their own competitor to Java, they dropped all of these weird types, and they all have very specifically different names. The thing is when C was first invented, an int wasn't necessarily 4 bytes long. An int may have just been 2 bytes long. And a short may have just been 1 byte long. And it differed on a platform by platform basis. You know, if you wrote your own C compiler, you could pick whatever number of bytes per value you wanted to. And it's standardized now. If you're going to write a C++ program and adhere to the modern standards, then you're going to follow those values. But they didn't have to have been that way. So I think it's worth lecturing just a little bit on the difference between an unsigned and a signed integer. I can type it. So if you have a 4-bit number, this is what it looks like to count in binary. I've counted the numbers 0, 1, 2, 3 so far. I'm going to keep going. It's like an odometer. I add 1 to that column. All right, and now the next series is going to be the same, except the first column is going to be 1s rather than 0s. If you're using unsigned ints or whatever, then once you go to 1,000, that's an 8, that's a 9, that's a 10, that's 11, 12, we're getting close to the end, 13, 14, 15. Unsigned means you're using every bit available to you in order to hold a positive number. So the possible values are, for 4 bits, can hold the values between 0 and 15. And we see those. Signed 4 bits are different. The first bit indicates whether it is positive or negative. And this is a simplification. It's not exactly true, but it's kind of true. So if you have 0, 0, 1, 1, and that's a 3, then if you change that first bit to a 1, that becomes a negative 3. If you have 0, 1, 1, 0, what is that? It's a 1, so that's a 2, and so that's a 4, so that's a 6. So theoretically, a signed bit, a signed number that had that would be negative 6. Now the reason why I waffled on it is because, well, here, let's just do this again. I'm going to take all these numbers, but I'm going to do them as though they were signed rather than unsigned. So I'm going to paste them down here. These are all the same, because if the first bit is 0, nothing changes their behavior. But here's where things start turning different. If a 111 is a 7, then putting a 1 there makes a negative. If a 1110 is a 6, then putting a 1 in the first place is a negative 6. That's a negative 5. That's a negative 4. That's a negative 3. That's a negative 2. That's a negative 1. And here we get into something weird, a negative 0. This style is called 1's complement. I forget whether it's an I or an E there, but there we go. Where the only thing you have to do is to flip the first bit, and then all the rest of them stay the same. There's also something called 2's complement, where you both flip the first bit and then you add 1 to the value. And that stops you from having both a positive 0 and a negative 0. But it's easier to understand if we just talk about 1's complement. Just realize that in real life it follows a slightly different standard, but the same idea. Why do you do that? Because now you can go negative. With these 4 bits, we could go between 0 and 15. Now we can go 0 to 7 and also up to negative 7. So we can go from negative 7 to positive 7, effectively. If we count those out, that's still 15 values. It would be 16 if we counted negative 0 and positive 0 as 2 different things. But, you know, that's a range of 15 values. But they're only half as big as these were, right? Because this one got up to 15, 0 to 15. But this one goes negative 7 to positive 7. You see what happened? We lost half of our magnitude, but the benefit was is we could also have negative values. So that's what signed and unsigned mean. You don't have to put the word signed in front of your ints, but you can put the word unsigned and it changes its behavior. An int can hold the values of negative 2 billion to positive 2 billion, whereas an unsigned int, the positive value, the largest value is twice as tall, but the bottom value is 0. For a long int, whatever that is, negative 9 quin super 10 tillion to positive whatever. Whereas if it was unsigned, you get twice as large of a maximum value, but the bottom one would be 0. That's what signed and unsigned means. For the most part, you're not going to care. You could be, you know, real picky and make all your counters unsigned because your counters are going to never go negative or whatever, but why bother? If your number is going to get bigger than 2 billion, then rather than make it unsigned to get to 4 billion, why don't you just make it a long? Then you have a much larger value you can play with.
Good. Type out long int.
Believe it or not, yeah.
Oh.
I know. I really wish that they had just made a long int, that one. I have no idea why an int and a long int are the same thing. That's ridiculous. But at some certain point, there must have been some argument in the definition committee. Okay, so we know how to define variables. You give it a type, you give it a name. If it's got a special property like unsigned, you put that in front of the type. You can define more than one variable on the same line, though. I could go in here and type int x, y, and z. That creates 3 variables all at the same type. But they have to all be the same type. I can't make x an integer, y a float, and z a string like that. Yeah, I could do this. Int a, float b, string c. But that's cheating because those are really 3 completely separate statements. Every time you hit a semicolon, the computer treats that as though, you know, those are 3 separate statements. If you have a whole bunch of variables in your program, you know, if you have 6, 7, 8, 9, 10 different ints, sure, you could put them all up here. You know, speed of light, whatever, you know, velocity, whatever. You could list a million of them. But really, it's kinder to your coworkers if you put them on separate lines, unless they all just serve very similar purposes. X, Y, and Z might be 3 different coordinates for, you know, a 3D space system. In which case, yeah, knock yourself out. Do it like that. And then put a comment, coordinates. But if it's 2 completely different stuff, like you have a counter and then also you have an interest rate, and then you also have something, you know, which looks pretty inexplicable. We don't even know what a JLP is. It'd be much cooler to do this. Int C, that's a counter. Int interest, really your interest is going to be a float, but whatever. You know, and say this is annual interest rate. And then int JLP. Only God knows. Whatever. So, yeah, you see what I mean. You don't need to deliberately, it's not mandatory to list all your variables in one line of the same type. It's just a convenience, which you can take use of or forget. If they're of similar meanings, go for it. Otherwise, if you separate them, you get a chance to document each one. Whoops. I want you over here. All right. Variables of different types must be in different definitions. Width and length are both ints, so they could be on the same line, but area was not an int, it was an unsigned int, so it had to be on a different line. We know what a literal is. It's a number that's typed literally into the program. If it has no decimal points, it's a integer. If it does have a decimal point, it's a literal float. By default, they're integers. If you need to make it a long, then you suffix it with ls. And why would you need to do that? What if I have a really big number? Long int, the debt of the United States is 30 billion, 30 trillion. A trillion has 12 zeros after it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Something like that. It's giving me an error. Yeah, right, prove me wrong. I got an error when I tried to build it, so I go down to the error list and I look. It says error. It gives you a code. You can always Google that code if you need to in order to find out what that error was. It gives you a line number, 10. You can just double click on the error and it'll take you to that line number. And it says A1 _ redefinition. And I look and yeah, I tried to declare two variables with the same name. My fault. I delete that. What's the next one? I usually fix them one at a time because sometimes you fix one error and then 100 go away. So now I'm going to build it again. Worked. See what I mean? It showed two errors before, but by fixing that one it worked. Okay, I'm going to run it now. Well, paint me yeller and call me a taxi. In some languages, such as Java, any number that you type, any literal that you type is considered an int. And if you type in a number that's too large to be an int, it calls it a syntax error. And you have to fix that by adding a suffix to it. An L to make it a long, or an LL to make it a long. Now Java doesn't have longs, so you just use one L. I thought that since this was larger than an int, since it was in the trillions rather than the billions, that I was going to have to suffix it. Let's read this slide and see if it gives an example of it. To store an integer constant in a long memory location, put LL. Oh, doesn't say why. If you want to do base 16, you put a prefix. We talked about hex, right? We did the worksheet about hex numbers. Okay, so if I wanted to type in a hexadecimal number in my code, I could do that. I could say that the debt is equal to OX FFFF, whatever. That happens to equal 3,500 and something. 35,000. So anyways, this is actually a number. It's just a hexadecimal number, you know, and it has some decimal value. I wonder if Google will do the translation for us. I could print it out. It will tell us. Yeah, it's 65535. So if I turn around and print out that variable debt, it'll say 65535. There. Now, why would you enter values in as hexadecimal rather than their decimal equivalent? Well, if you're dealing with hexadecimal data, you may not want to do the little brain trick to convert it over. There's also the ability to force it to be an octal number, which you just put by putting a 0 in front of it. Debt is equal to 0, 300. Now, you might think that that means 300, but that's an octal. So if we print out the debt, it's not going to equal 300. It's going to equal something else. Octal is like hexadecimal, except it's only got 8 possible digits. So you only have the numbers 0 through 7, and you don't have an 8 or a 9. And nobody uses it anymore. I'll say that. Of course, somebody does somewhere. But anyway, so I ran it, and octal 300 is 192. And if we wanted to see why, we could. So remember when we were dealing with decimal numbers, base 10 numbers? The first place was 10 to the power of 0, the second one was 10 to the 1, the third was 10 to the 2, and the fourth was 10 to the 3. So that's your ones place, that's your tens place, that's your hundreds place, and that's your thousand place. Hexadecimal, 16 to the power of 0, 16 to the power of 1, 16 to the power of 2. I'm only going to do 2 of them. But that makes this the ones place, that makes this the 16s place, and that makes this the 256s place. So 300 in hexadecimal, if I wanted to figure that out, that would be 3 times 256 plus 0 times 16 plus 0 times 1. Whatever 3 times 256 is. Octal. 8 to the power of 0. 8 to the power of 1. 8 to the power of 2. Well, anything to the power of 0 is a 1. 8 to the power of 1 is an 8. 8 to the power of 2 is a 64. So the number 300 in octal, we want to convert it. That's 3 times 64. Somebody want to punch that in their calculator? Figure it out in your head. Plus 192, you said? 392? 192, okay. And there's no 8s and there's no 1s, so it's just 192. And so when we printed it out, let's see if that's what we got. Yeah, that's what we got. I'm not going to ever ask you to convert anything to octal. Its purpose was somewhat similar to hexadecimal, but it's clusters not of 4 bits, which hexadecimal numbers are, but of 3 bits. I did not mean to make the text gray. What happened there? All right, this is boring. Let's do something more fun. So, out of the in-class assignments we've done, which I believe are only 2, we have a PayOne program. Let's go look at what somebody's PayOne program looked like. You gonna download it for me? Here's what this one looks like. It has an hours and a rate and a pay. How many hours did you work? We type it in. How much do you earn per hour? We type it in. And then we do a pay and we print that out. Pay is equal to hours times rate. Now some lucky devils get paid for more than 40 hours overtime. Maybe you don't get benefits or something, but you get your time and a half. Which means that for every hour over 40, you get a bonus of half again. So we're going to take this kind of program right here, and we're going to modify it, and I'm going to just type it all in again, so it's not like you have to go and find your old one. And modify it to do time and a half. All right, I have a lot of garbage up at the top of mine. You may have been typing in garbage too. Just somewhere, create a new file. If you're not already in a source code file, I mean, or just scroll down to the bottom of the one you already have going. And let's declare some variables. We need a float for our hours. We need a float for our rate. Let's declare a few more. A float for the total, a float for the bonus, and then one more float for the paycheck, which is equal to the total plus the bonus. So we're going to use those variables. We may as well initialize them all to 0. I like giving initialization. I like setting things equal to 0 as we create them. That way, if I have an if statement that sets it to a different value, I don't have to write an else that'll set it to 0. That'll come into play for the bonus. You know what? I'm not sure that any of this was of any use. I'm just going to take all of this stuff, delete it, and just paste it in a notepad, leaving our good code. So there we go. Our normal looking code. The only thing missing is that I usually also do # include string, but we're not using strings this time. All right, let's calculate their total. Total is equal to the hours times the rate. Now let's display. Oh, we haven't even put any input in. I'm so sorry. Delete that line or something. Okay. Display a message using cout. Enter hours worked. Colon. And then cin into our hours variable. Let's do the same thing for the pay rate. Cout. Enter pay per hour. Cin into the rate variable. Now that we've got that information, we're ready to calculate the total. Total is equal to hours times rate. Let's print it out. Cout total equals, and after the quote we're going to put 2 more arrows and total, and then followed by ENDL. So it'll go to the next line if we had something else to print. All right, I'm going to test that out. This doesn't meet the requirements because we wanted to support time and a half. So 40 hours a week, $10 an hour, total 400. That looks good. All right. We want to modify it so that we support that additional clause, additional rule. What we want is the bonus being equal to, or set bonus, don't ever type the word set, that's pseudocode, set bonus equal to hours over 40 times the pay rate, but it's only time and a half, it's not double hours, so we have to divide it by 2. We need that in there, but it's conditional. So we're going to need an if statement. An if statement looks like this: if A is greater than 3 or something like that, or if X is less than 5 or whatever, and then you put some stuff inside quotes. So with those two pieces of information, that this is how you calculate the bonus and that this is how you do an if. Now we obviously don't have a variable named A. That's just an example. Think about how you would modify your program to calculate the bonus, but only to calculate it if the hours was greater than 40. I will be right back. I'm so sorry. 2-minute interruption. Oh, and I'm also sorry that I blew away the screen before you could finish typing it. Sorry about that. So we added that underneath the total. We've added these two. Well, one of these. Now let's do the paycheck. One more C out. Paycheck equals arrow arrow paycheck arrow arrow ANDL. So the obvious place to calculate the bonus is certainly before we try to add it to the total. So let's do that here. I'll give y'all a second to keep typing. All right. Who has an idea? What should we put there?
So you do if, in parentheses, hours is greater than 4.
Okay, right. If hours is greater than 40, then what goes in here?
Well, you could say like bonus equals, in parentheses, hours minus 40 times the rate divided by 2?
You are correct, because we only want hours more than 40. So we can't just say hours times rate divided by 2. We only want this rate, this bonus, to apply for every hour over 40. So we're going to do this. Bonus is equal to hours minus 40 times rate divided by 2. Now this is the point where I've gotten into arguments with students who had it in their mind different ways to calculate time and a half. And I'll totally say there are different ways to calculate time and a half. But this works. This is one method that works. There's another one. I'm not going to go there, but there are other ones. So that is how I would do it, and that's probably how you did it because that's what I set up, you know, in my example, or that's how you think of it as well. This should work. Let's give it a shot.
We don't need a then statement.
You mean an else? There's no such thing as a then, actually. We say then, but it's not actually a word. If I type in then, it's not going to work. There's no such thing as a then. This is the then. And I'm sorry if I've said then too much and made you think that it was actually a part of the programming language. It's not. So if hours greater than 40, then hours is equal to that. That's how I say it, but you don't type in the word then. Some people, once they get used to the idea that there are also else's, want to put else's on everything. You could do this. You could say if hours is greater than 40, then bonus is equal to that, else hours is equal to 0. That's totally legit, but we had already declared hours and set it equal to 0 up here. That was supposed to be bonus anyways. Yeah. Okay. So let's try it out and see if it works. No build errors. I'm going to run it now. Enter hours worked. First, let's enter something that doesn't get a bonus. You can work up to 40 hours and not get any bonus at $10 an hour. The total is 400. The bonus is 0, so the paycheck is 400. Let's do it again. Hours worked. Let's do 50. So we have 10 hours of overtime. So our total was 500, but we got a bonus of $50 because 10 hours times our pay rate of 10 would have been 100, but we only get half again as much, so it's 50, so our paycheck is $550. Everybody got that?
Mine didn't run, so I had C out errors.
Let me come look at the video. So just in case you don't have it up there, make sure that you have a main method declaration and your include and your using. And down at the bottom, if you're using Windows and not Mac or Linux, you're going to want to stick a system pause down there. What we're going to do is to write a BMI, a body mass index calculator. Now the idea behind BMI, and it's pretty much a crock, but we're going to go with it anyways, is that your BMI rating in general tells you whether you're underweight or overweight or within the normal range. Now on a person by person basis, it doesn't really mean a hoot because it doesn't take into account muscle mass versus, so football players, they could be incredibly lean and ripped and it would still say that, oh, you're obese because your BMI was too high. So don't take this as meaning much of anything, but on a statistical basis. If you say, okay, this city, most of the people in it have a BMI of 30, and this city, most of the, or in France, this city, everybody has a BMI of 20, then yeah, you can pretty much say that, okay, those people are thinner over there. So the equation for calculating BMI is this. It is a number a conversion ratio, which I don't remember yet, so I'm just going to call it X, times your weight in pounds divided by your height in inches squared, like that. Now I'm going to go peek at what I had.
Will that PDF be available on the Dropbox so we can see, like?
Well, that PDF had the answer on it, but I'm going to download. I'm going to upload.
Okay.
Yeah. I just didn't have the Word doc with the assignment without the solution, so I'm faking it. Okay, so the magic number on there is 703. That's what x is equal to. And if you're measuring in kilograms and meters, the conversion ratio is something else. So int, or double, float, x is equal to 703. Then the BMI is another float. So what does your program need to do? These are the equations for calculate it. How to calculate BMI. But you need to gather two pieces of information, which are what?
Height and weight?
Yeah, your height and weight. So have your program ask for their height in inches. If you want to be cool, ask them, no, that's good enough. And their weight in pounds. Once you have pounds and inches, do the calculation. Then display the result. And here's a sample. I don't want you to type this into your program, but it's a sample of what it might look like when you run it. Welcome to the BMI calculator. What is your height in inches? And you type 60. You're 5 feet tall. What is your weight in pounds? And you say, I weigh 100 pounds. I certainly don't. Now, then we would say your BMI is, and I don't know what that is, but we could type it out. Let's use Google to calculate it. Google's my favorite calculator. Alrighty, so it's 703.
Times 600?
Yeah.
Oh wait, that's not that simple. Never mind.
No, 703 times our weight divided by our height squared. 60 times 60. 19.5. So that person's pretty thin. 0.5, whatever. No. And for the curious, the range is 25, is, beyond, above normal, and above 30 is considered, way more overweight, and below 17 or something is like where you're seriously, getting a little bit too thin. So, like I said, it doesn't mean a lot, but it is a statistical calculation. So, this is what I want the program to output, or sample input output. The result is not exactly what you will get. All right, that makes sense, y'all?
Yeah.
Pretty easy program. You may be able to write it, like in 5 minutes. It may take you longer. It's okay. All right, gang, let's do a Dropbox so you can upload your Pay2 program, and then we're done.